alkenes, and we are talking about electrophilic addition reaction. Yesterday we learned one of those electrophilic addition is formation of vicinal diol, having two OH group on the two neighboring carbon, which it is extremely important reaction in making natural products that you and I call them carbohydrates, glucose, those kind of things, guys. Now that being said, the reactions that we were doing, epoxide, ring opening, always is going to be, when it comes to stereochemistry, always is going to be what, guys? Anti. So the two OH are going to be opposite, which has effect on the stereochemistry of the stereocenter that we are producing. Now, when it comes to natural products, some of those OHs are anti or anti, depending on your nationality. Some are on the same side. So we need to make both anti and syn. So today we are going to talk about making syn vicinal diol. Well, in old days, the only reagent we had was permanganate potassium. Question. Can I write plus enantiomer for this particular reaction, for the one that you are seeing on the board? Can I write plus enantiomer? Why not? This meso, plane of symmetry. Of course, if you had a pre-existing stereocenter, then I would write what, guys? But here, there is not any pre-existing stereocenter. Stereocenters are produced as a result of the action. You have a plane of symmetry. Your compound is meso, so it is not optically active. Now, that being said, permanganate potassium is one of the very, very strongest oxidizing agent that you can ever have. Permanganate potassium at least is as strong as Jones and PCC. Do you remember, guys, Jones and PCC? So, permanganate potassium is at least as strong as they are. So what that means? It means that when it comes to permanganate potassium, you get alcohol. And the reason I reminded you of Jones and alcohols, because these were the reagents that you use, Jones and PCC. These were the reagents that you used in Chem-1 18A to oxidize alcohols. So what it means is that with permanganate potassium, it is possible to have over-oxidation. So, when it comes to permanganate potassium, it is possible to have over-oxidation. And what will happen when it oxidizes? Literally, it breaks your carbon-carbon double bond. And in this case, you are going to get a dioic acid, carboxylic acid gas. So this is the problem with permanganate potassium. Commonly, you get a little bit diol, vicinal diol. That you have to be very careful. You have to watch the concentration. You have to watch the temperature very carefully. And the reaction already is exothermic reaction, something that it is not in your control as much as you like to watch it. It's not in your control. So this is the problem. So in past, yes.
Professor, usually when you oxidize, you form a bond because they're short electrons, so they have to bond, correct?
I'm sorry, it is on.
Oh. Change the battery?
No, it is on.
Oh, okay. But it's not
So
working?
it's the microphone.
Oh.
My apologies, so I even don't know why I am pretending I have one. I am sorry, guys.
That's the only one in the electrol 1100. Goodness, yeah.
Okay, guys, I don't carry cell phone with me. Does anybody have cell phone? Of course.
I'll call the... Who do I call?
752-33... Of course, it's area code 530. 752-3333. And let them know.
Yeah. I'll let them know that one doesn't work for 1100 also. Yeah, go ahead.
Thank you. Okay, so hopefully help arrives. Now, due to the fact that, as I said, these are natural products, and it is important to be able to make them in past century, a lot of research has been done to find the right oxidizing agent that can oxidize carbon-carbon double bond up to the point that you want. And once it made the diol, it stays away. The one that has been found is osmium tetroxide. When you look at osmium tetroxide, permanganate potassium, guys, okay, either sodium or potassium. So this is active ingredient in permanganate potassium. When it comes to osmium tetroxide, pretty much similar structural features. So, osmium tetroxide is the one naturally nature does not make it. It is being made. And it is the one that does not oxidize the alcohols. So we don't have to be concerned about over-oxidation. The only drawback to osmium tetroxide is, first, it is extremely expensive. Very, very expensive. And second, it is highly toxic, poisonous compound.
Yes, Professor, I believe they use this in nuclear bombs. They use osmium for something. That's probably why it's so expensive.
Yeah, that's the field that I am not familiar, guys. I'm organic chemist. I want to build for the better. Okay, so that being said, this is something, with Perez we have the ability, because trust me, we will save every particle of the compound. And we have learned how to get it back. So the Perez is no longer issue. That toxicity, we cannot do anything about it, except when we are working in hood, we make sure that we have a functioning hood, and there is no outflow. It is all inflow, and to get it up. So, because the mechanism for both is the same thing. With slight differences. Commonly, with permanganate potassium, just doing the reaction in water is good enough to get the final product. With osmium oxide, it is not. With osmium oxide, I'm sorry, of course, osmium tetroxide to be correct. Sorry about bad handwriting. I don't want you read it as sulfur, guys. Osmium tetroxide. When it comes to osmium tetroxide, we have to do the reaction in two steps. First, oxidation, followed by reduction. And when it comes to the reduction, many sulfur compounds are good. Hydrogen sulfide or disulfides, they do the reaction. Okay, so this time now, obviously, as you can guess, for the purpose of communication, this time I'm going to show this. Now, if that's the case, what would I write, guys? Plus diastereomers. Okay, so be careful. Now, I am only showing you the mechanism of oxidation. The reduction is a little bit more involved. We do not get involved. It won't make any difference whether you use osmium tetroxide or permanganate. The mechanism of oxidation for both are exactly the same. Don't forget, we are talking about electrophilic addition. So when it comes to osmium, I don't have to tell you, it's oxidation state. Here is 8. Strong electrophile gas. So that is the driving force, that when we are bringing the pi electron, another familiar feature, osmium is electron deficient. So you will see another familiar feature. You give electrons with one hand, you take it away with the other. And when you do a reaction in one step, always is going to be seen. It is not possible to be any other way. Any reaction that it is in one step is going to be, with carbon-carbon pi bond, is going to be seen.
I have a question about the arrows for the first bit.
Yes.
The arrow for the lower oxygen, that is supposed to be coming from the bond?
That's what you are doing.
Okay, just making sure that I'm...
Thank you. That's why I am writing single bond. And I'm going to put, generally, remember, remember, you and I don't put electrons. This time I am putting the 2 electrons on osmium only for one reason. I want you are noticing it's gaining electron. If it's gaining electron, it means it is being, guys, reduced. That's what it means. Thank you so much. I really appreciate it. Did you hear him when he was checking?
We borrowed
I shouldn't. That's right. I'm checking. Okay. Sir? Sir? Sir, there is something wrong with system. It's not working.
That's why it has to be paired, like a Bluetooth or something. Have to pair up. Interesting. Thank you.
I see.
No.
No, I need to.
Okay, so what is happening? We are obviously oxidation. We are oxidizing carbon-carbon double bond. Yeah, now I can feel it. Okay?
Thank you very much.
So, I guess the volume now is too loud. It cannot be in this room. After oxidation, then it becomes the next step. We have to add the reducing agent. As I said, either NaH or hydrogen sulfide, H2S, either would work without any problem. And this is the one I'm not going to show, the mechanism, because it is truly general chemistry, and it's not worth your time and my time to go back and review redox reaction all over again. Which osmium is going to be totally reduced from positive 8 to positive 4, as you can see. Now, remember that is the one that will oxidize. This one doesn't do any good. We need it. So common practice is, and I'm going to be honest with you, any person, any scientist who use osmium tetroxide will save every particle of this compound for 2 reasons. First, if you want to get rid of it, waste refusal, it costs us more to dispose it than keep it. I'm not kidding. Because, for example, in lab, you are using dichloromethane as solvent. Let's put this. The price that we are paying to get rid of it is 5 times the price that we are buying it. These are carcinogen, toxic materials. They have to be handled carefully and those kind of things. So that's why generally we do the best if we can reuse over and over. For example, we still get again dichloromethane and use it instead of just getting rid of it. Really, green chemistry now is forecasting to do to the best of our ability to have less waste. Because again, nature does not make dichloromethane. We have to buy it. Not only we have to buy it, we have to make it. So, because we have to make it, it's better if we can recycle it, reuse it. With osmium tetroxide, which is extremely expensive, trust me, nobody is going to waste any particle. So commonly, it can be easily oxidized with hydrogen peroxide. It is commonly being oxidized with hydrogen peroxide. And so once one person in a lab buys it, use it, reuse it. for as long as they need it. And then when they don't need it, I'm not kidding, they advertise. You know, we have this quantity of osmium tetrax selling somebody wants, which you can see they get lots of email. You have to decide which charity is the best one. I'm talking about research group. So this is as far as one oxidation. The second oxidation is ozonolysis, which the title tells you what kind of oxidation is. Yes. What that means? Liberate it apart. So when it comes to ozonolysis, which we call it oxidative cleavage, again is being done in two steps. Oxidation followed by reduction. We are calling it cleavage. What it means we are breaking carbon-carbon double bond, and they are replacing it with carbon double bond oxygen. Okay, guys. So regardless of what we have here. Now what it means, guys, a compound that it has C double bond O, what it can be. Either aldehyde or ketone. Okay. So basically what it means that we can make aldehydes and ketones from this reaction. For example, if I do this reaction, the carbon that has hydrogen becomes aldehyde. The one that doesn't have hydrogen becomes ketone. Okay, guys? So we can get aldehydes and ketones from this reaction. So how does the reaction work? By the way, step 2, you have two choices because it is a reduction. You can either use dimethyl sulfide or you can use zinc in acid and commonly if you are using acid you are going to use the cheapest one, acetic acid. It does two things. First, solvent. Second, also the acid that it produces hydrogen. Don't forget, zinc is reactive. React with metals produces hydrogen. And that's the hydrogen that will reduce the next step. So how does the mechanism work? The structure of ozone. only structure that you are going to have for boson is going to be this. Don't forget, reactions of carbon-carbon pi bond is electrophilic addition. So we need electrophile. Now, we have 3 oxygens. Of the 3 oxygens, which one would you expect to be more suitable as electrophilic oxygen gas? Okay? Because you have choices, that's what you think. But, that being said, if I take the middle one, remember these are the reactions that are electrocyclic. We give electrons with one hand, we return with the other hand. Is that that? Electrophilic addition is that. Now, if I take this oxygen, that comes here, and this oxygen comes here, how many member ring? How many member ring, guys? You have 4 atoms, don't you? 1, 2, 3, 4. Now, on the other hand, if I give the electrons to this oxygen and use the other oxygen, how many member ring? 5. Between 5 and 4. Which one?
Yes.
This oxygen, if I use this oxygen, I would get 5 member ring. I get it? 1, 2, 3, and the 2 carbons, 5. So between 5 and 4, no contest for member rings are not very stable. 5 member ring, 6 member ring, guys. Keep in mind, generally, when we are doing electrocyclic reactions, if it's possible, my first choice is 6 member. My second choice is 5. Okay, guys? When it comes to 4, is not very favorable. When it comes to 3, is even less favorable. So unless we don't have choices, we go to those. And some of them never happens. So, what will happen? Naturally, you are going to have electrocyclic reaction. You are taking your pi electron, and naturally you are returning to the other one. Non-reversible reaction. So this is electrophilic addition. Electrophilic addition is that. Now look at my 5-member ring. As 5-member ring is stable, that would it be stable as a compound? Look what you have. What do you have? 2 peroxide bonds. 2 peroxide bonds, not 1. 2 peroxide bonds, which naturally are not stable as all. So this is what is happening. Peroxide bonds are not stable. They are breaking apart. So what will happen? I am breaking my carbon-carbon bond. Are you noticing, guys? To the best of my knowledge, until today, any reactions that you did with carbon-carbon bond was bond making. For the very first time, we are breaking carbon-carbon bond. And because we are practicing, we do such a good job that not only we are making carbon-carbon bond, we are breaking carbon-carbon double bond, as you can see. So what will happen? So this is first step. I want you to notice the first step, we are going to get ketone. And we are going to get a species that, again, it is common knowledge. It's not stable. Why it's not stable? You have peroxide bond. And not only you have peroxide bond, one of your peroxide oxygen is tremendously unhappy. Not only is peroxide, it is also positively charged. So what will happen next? Well, I don't have to tell you that when it comes to C double bond O, C double bond O is electron deficient. Do you remember chapter 8, making alcohols? You use aldehydes, you use ketones to get larger alcohols, guys. If you have forgotten, please go back and review chapter 8, synthesis of alcohols. C double bond O is electron deficient carbon. This carbon specifically is highly electron deficient for obvious reason. Not only it is bonded to oxygen, which is electron withdrawing, the oxygen is electron deficient as well. So what will be next? Another nucleophilic addition. Now this one is a nucleophilic addition. It starts with nucleophile, which it means you are giving the electrons back to positive oxygen. That now, as soon as you take those electrons, what happens to this carbon gas? This becomes now more electron deficient, because again, this one is going to happen. And again, remember, 5-member ring. Okay. So you are coming with a new 5-member ring. Non-reversible reaction. This 5-member ring, you have oxygen, which it is flanked between your two carbons. Okay, guys? 5-member ring. In this 5-member ring, one of the oxygen of ozone is flanked between the two vinyl carbons. So this is step 1. We took care of one of peroxide bond. What is there, guys? Still a peroxide. So what will happen here? Now your reducing agent will get in action. Okay, that's that. If it is hydrogen, it will be hydrogen. If it is dimethyl sulfate, it will be dimethyl sulfate. And what will happen? I am going to write the structure higher. You do not need to write it because I have no doubt you have enough space. I just want to put that higher enough that you all can see it. So, the next step is reduction, step 2. And I'm going to tell you, sulfur, dimethyl sulfide is very popular, and you certainly will see Hawaii. Again, I repeat, you can use zinc in sulfuric acid. This stage wouldn't make any difference. This is more popular. So what is happening? I have a peroxide bond needs to be broken. Agree, guys? We have a peroxide bond needs to be broken. And it happens that sulfides, hydrogen sulfides, they are reducing agent. In biological system, they have proven they are reducing agent. So this is something that will happen. You are giving 2 electrons to your peroxide for obvious reason, because you need to break the peroxide bond. Okay. Now that I am trying to break the peroxide bond, you and I know oxygen, nitrogen, carbon, they can never ever have 10 electrons. So if you are giving 2, you have to take away 2. Now that you are taking 2 away, that carbon cannot have 10 electrons. Guess what? You have to break that. Now that you are breaking that, then what? This cannot happen, so what will be next? So when the reaction is completed, your dimethyl sulfide becomes dimethyl sulfoxide, DMSO. I don't know if you remember, chapter 5, one of highly polar aprotic solvent, excellent for SN2 reactions, guys. So truly, this is the reason that commonly dimethyl sulfide is being used, because they shoot 2 birds with one stone. Both organic products are valuable. By both, I mean the sulfoxide DMSO. It is expensive solvent. So I'm going to make expensive solvent plus aldehyde or ketone, or in the case of example that I have used, both. So these are as far as the chemistry of chapter 12. Now, when it comes to electrophilic reaction, when it comes to organic chemistry, there is a possibility that we have a compound that it is diene. What diene means, guys? It has 2 carbon-carbon double bonds separately, is that right? Or triene or so forth. So what will happen if I am going to use a compound that it has more than 1 carbon-carbon double bond, and I am using a limited amount of reactant, basically 1-to-1 ratio. Then if I have 2 or 3 bonds, the question is which one is more reactive, which one is less reactive. Because here we are talking about electrophilic addition. Which carbon-carbon pi bond is more reactive? Which carbon-carbon pi bond is less reactive? The common practice is, guys, when it comes to trend in reactivity, the more substituted alkene is, even though it is the most stable, it is the most reactive as well. Keep in mind, stability doesn't mean inner. Okay? Stability means it has more chance to form, more chance to exist. That doesn't mean less reactive or inner. So when it comes to electrophilic addition, the more substituted double bond, the more reactive double bond for all reactions except hydroboration. Okay? So when it comes to electrophilic addition, except for hydroboration, generally the more substituted alkene is, the more reactive. What do I mean? Yes, I don't think anybody needs the only one needs to know it is me, exactly, because you already have them. So what it means is let's take this dye in and react it with and I'm going to write one equivalent. One equivalent means 1 mole. If you start with 1 mole dye in, you have 1 mole per oxycarboxylic acid, which it means I don't have enough for both high bonds. So if that's the case, A, what is the major organic product? Second, B, which bond? Okay, guys? So in this case, what would you expect? What is the name of the major organic product? If you do this reaction. I don't want the name of the compound. I want the name of the product, the generic name of the product. What would you expect to get, guys? If you use peroxycarboxylic acid and alkene. It was yesterday's lecture. And please don't tell me I am studying this class or not, because you should say right away epoxide. Okay? Alkene, peroxycarboxylic acid, epoxide. So now, if it's epoxide, which epoxide? Right or left? Double bond. Yes. Has to be the right one. Like the right one, that's the one that it is more substituted. So in this case, the major organic product will be the other carbon double bond is going to produce only 9 gas. Now, on the other hand, what would happen if I do hydroboration? Which of the two carbon would you expect to react? The left one. Because hydroboration, due to its nature that boron really is not seeking electron, doesn't go towards the more substituted. Always goes towards the less substituted. So in this case,
The question?
yes.
Is that because of less hindrance? What's the real reason, Professor?
Well, I cannot use hindrance because the transition state
Okay.
for both is called the transition state. Experimentally, we have learned that boron always is aiming. Boron always is aiming to the less indirect side, guys. This is absolute experimental. I cannot use any excuse because if you go back and look at the mechanism for both reactions are electrocyclic. So when it comes to your electrocyclic, both are the same. So I cannot really come with a reason other than telling you. I can understand why the more substituted alkene is the most reactive one. Obviously, electrophile 6 electron. If you are fundraising, guys, are you going to go to a rich person or a poor person? Is that right? Rich person can write a check larger. Even though not always true. Not that, they tell you right away. They say, oh, I have in bonds and stone, and you have to wait until they get mature so they know you are not going to work with it. But generally, truly, I'm going to be honest. Any researcher that I know, the first thing that they would apply is NIH. Then they will go to the others, and they will check the companies and see their histories of which one they give more away. So, the same thing. The electrophilic addition, electrophile first knocks at the door of rich alkene, guys. Substituent pushing electrons. The pi one is richer. Boron is the only one that doesn't like electron. Do you remember? The only electrophile that is electrophile that doesn't like electron is boron. So boron always goes to another pole alkene, if you want to consider that. This is one. Second, when it comes to carbon-carbon double bond, without using spectroscopy, as undergraduate, I am aware you don't have access to IR anymore. What are the two tests that we can use in lab without any spectroscopy to identify the presence of carbon-carbon pi bond? Pi bond. It could be very important. There are two popular tests. And both of them are visual. By that I mean color change. The two visual ones.
Didn't yesterday you said like the bromine, the BR2, it's brown and then it is.
Somebody is listening to me. Okay, guys, I need thank you so much. Hey, when I'm asking you, I don't want to answer the question myself. I am testing you to see if you truly are studying on them the way you are telling me, constantly, all the time. And so when you are replying, then that tells me, oh yes, these people are teaching. And I'm going to tell you, and this is something experimentally I have noticed. The more interaction students have with the class, the higher the class average is. Last year, I had a class, and for whatever reason, the students decided to stay with me for the entire year. And I'm not making this up. They took 118A. More than 70% of them, they took 118B. And all of them, because I told them last time, unfortunately, they had no choice. They had to take a 118C with me. And the only reason they had no choice, the department assigned both 118C to me. And neither them nor I had choice. I didn't want to teach 2 sections, and probably some of the students didn't want to be with me either. But now, you know, I am going to say that, and they are nice. They are constantly staying in touch. They send emails. And as yesterday, one of them said, I really am so happy that I had all of my study, and I replied, 118C, you had no choice. So that means that truly, they were very, very interactive. And I had 33% A, 33% A, and heard of in Oaken during the spring quarter. And I'm talking about guys, over 700 students. I'm not talking about that small group that you say is exception. So that's something to prove to me that, you know, we don't give A and B, and that's what I write on my syllabus, because you understand, instructors feel that it's great information. Honestly, I don't feel that. The same time that I don't feel it's great information, I have had classes that I have only 4% A. So I want to know, because everybody knows me, knows that I, from day one, tell the students, these are the cutoffs. If you compare the exams, the level of difficulties are similar, truly. Of course, I do understand that any kind of student takes a test, feels that the test was harder than practice. And I truly believe that for one reason. When they are taking practice tests, they don't feel it is a test. They took it as a luxury. They want to take a coffee break, they do. They want ice cream break, they do. They depend on that. When it is exam, it's only 50 minutes. And one thing I'm going to tell you, I tell the TAs, never ever make any announcement that 5 minutes is late. If you want to write on the board the time, that's fine. But honestly, I tell them, because I don't want. They make you nervous by saying, oh, 5 minutes is late. And come on, mister, you can check. You know what time it is. Am I correct, Lisa? You don't need additional studies. That I have taken exam. I have grader. I wasn't born as instructor in chemistry. I have been sitting there. And I'm not kidding. I still vividly remember I was taking the Oaken exam. And I looked at the question and I said, have I ever seen this? And I'm not kidding. Every 5 minutes or 10 minutes I was looking. And again I was questioning. When the instructor has hit me, this was to me, you know, I was like a deer with light in eyes. And all of a sudden, the professor said, 5 minutes left. And believe it or not, I have not answered 80% of the questions. And I have 5 minutes left. And of course, I didn't do good on that test. I'm not going to lie. So I have taken Oaken, and I have read it. And later on, as soon as I left the lecture room, 5 minutes left, you know, it's kicking time. You kick yourself. Oh, that question was that mechanism. Or that question was hydroboration. Ring opening. You know, one after the other. Then, I don't know what you're up to there. I still, when I think about that, I'm saying, how could you be so stupid? And I still don't have answer. That I know it can happen. 50 minutes truly, I know it can happen. That's why you want to telling yourself the only reason I'm asking you questions, guys, is not wasting your time. It's only bringing to your attention that you have, in autumn, you have to do your study ahead of schedule. And almost always be sharp so it becomes intuitive. Autumn has to become intuitive based on the concept. So, yesterday we said boromine is the most popular halogen because first it's liquid, second, always is color visual. You go from brown solution to clear solution instantly, truly, as soon as the drop of boromine hits your reaction. If it reacts, the color disappears. So boromine is one. What is the second one? The second one I mentioned today. Permanganate potassium. Permanganate potassium also is, guys, so when it comes to double bond or pi bond, not double bond because in 5 minutes I'm starting to talk about triple bond. Pi bond. Oh, I wrote color, that's why I didn't write solution. With boromine, I wrote brown solution. With that, I wrote colorless, that's all I wrote. Why I didn't write solution? All hollow alkanes, water soluble. Okay? So solution is, they are dissolved. Hollow alkanes are not water soluble. And so also there is going to be physical change, not only in color, in phases. So that's something that also. The other is permanganate potassium. Do any of you remember the color of permanganate potassium from your general chemistry? It is purple. Absolutely. Pink purple, yes. It depends on, no, it depends on concentration. If it is dilute, it's more pinkish. If it's concentrated, it's more purplish, guys. This one, it is color. Because, don't forget these transition metals, can you see? Their colors is depending. So, depending on the ligands, how many waters you are going to have, those kinds of things. But when you are getting your diol, no, permanganate potassium is more advantageous in identification. However, permanganate potassium is more advantageous, guys. If I am color blind, would I see change color? But would I see change of state? Manganese dioxide or manganese 4 oxide is not water soluble. As you see solid, you see truly brown, dark brown particles start floating to settle. And so these are the two popular tests that commonly are being used to identify a carbon-carbon pi bond in a molecule. So with that, we are moving to the next type of carbon-carbon pi bond, and that is alkane. So it is not secret that alkynes are carbon-carbon hydro. Now, that being said, I'm going to ask you classify, rank these three compounds in order of increasing acidity. Now, do you want one be strongest or weakest? So one strongest, guys. So rank these compounds in order of increasing acidity, such as 1 is strongest, and naturally 3 is going to be weakest. And you don't have to give me their name, just say, alkene, alkane, alkyne, as either weakest or strongest. So which of the three would you expect to be strongest in acidity? Alkyne. Which one would you expect to be weakest? And alkene, oh yes, they are going to be. Question. Why? Why? Alkynes are strongest among the three. Oh, by the way, I don't know if you have heard this vocabulary or not. Aliphatic, have you heard? Have you heard aromatic? Anything that is not aromatic, it is aliphatic. That's the very first classification of compounds in organic chemistry is aliphatic, aromatic. So why alkynes are the strongest acid among aliphatic hydrocarbons? Yes. For that. Electronegativity S character. There is it. Higher S character, strongest acid. Now, when it comes to naming, it is exactly the same as naming alkenes, with one exception. What is the exception? No cis, trans, or easy isomerization, guys. Okay, so it is exactly the same as naming alkanes. You subtract N and you add ein. Okay? Now, that being said, as you and I know, it is possible that we have compounds that they have two functional groups, three functional groups. It is possible. What is the order of precedence? So far we know three. The three that we know are obviously alcohols, alkenes, alkynes. What is the order of precedence, guys? We already know alcohol have higher precedence over alkenes. But now I'm going to tell you now, that being said, IUPAC has screwed up 100% when it comes to compounds that they have both double bond and triple bond. Okay, guys? Compounds that they have both double bonds and triple bonds. the domain bonds because as you know, carbon-carbon triple bond angle is 180, so not to be correct there. Okay. So, what do I mean that IUPAC has totally screwed up with naming compounds that they have both double bond and triple bond? First, I'm going to tell you they are, as we would expect, alkene ine. Am I correct? You have double bond, which it is substituent. Last name, triple bond has precedence. Now, commonly, if you are going to number a compound, please rewrite a new one. If you were going to number this molecule, would you number from right to left or left to right? You would number right to left. And if I ask you why, the answer would be because you want that your functional group has the lowest possible number. Always is the case except alkene. Now, when it comes to numbering, IUPAC has a rule. Okay? In numbering, the carbons of alkene 9 always number from the end that is closest to the pi bond.
Question?
Did I say double bond or triple bond? I said closest to the pi. So in this case, we are going to number from left to right, because the first pi bond happens to be bonded to terminal alkene. Yes. Now, what is the name of this compound? You have two options. Obviously, your alkene, is that right, is 1 in, and then it is 3 ine. How would I name this compound? I would name it as 1 pentane 3 ine. So I want to know, guys, either or correct. Now, the question is, what happens if both are the same distance? In and ine. What happens if both are the same distance? So now this time, from either end that I start, the first pi bond would be bonded to what number? From either end. It would be 2. So if there is pi, still IU part has decided to make both happy. How can it keep both happy? Last name always is going to be, yes, ein. So how could the other functional group be happy? It will get lowest number. So keep in mind, in naming alkene, rule number 1, from the end closest to the first type. In case there is pi, in gets the lowest number, ein always is going to be functional group. So again, in this case, still,
Did you say in or ein gets precedence?
last name always is ein. For numbering, that is pi, E gets lowest, ein always is last name, as you see.
Okay, in gets lowest.
In gets lowest. If there is pi, guys. If there is not pi, what is the rule? Closest pi. That's it. Closest pi. If there is not pi, the first pi one gets lowest number. If there is pi, in gets the number, the lowest number. Ein always, because you call them alkene, don't forget. Last name always is alkene. You are ending with ein. So this is the rule that I have to tell you. Naturally, in this case, it's going to be arct 2 in 6 ein. So these are as far as name. Now, when it comes to synthesis, one thing that I have to tell you is the chemistry of alkenes. And alkynes is very close in every aspect, synthesis and reactions. So first, when it comes to synthesis, how did we make alkenes, guys? By what mechanism?
Elimination.
Which one? A2. So when it comes to synthesis of alkenes, it is the same thing. Elimination of hollow alkenes. Except this time, it has to be dihollow alkenes. So when it comes to synthesis, it is going to be elimination of dihollow alkenes. It would not make any difference whether both halogens are on the same carbon. It would not make any difference whether both are on the same or each carbon has one. As long as the two vicinal carbons have a total of 2 hydrogens and 2 halogens, the reaction works. Now, that being said, time we are using stronger base. We are using amide. Don't forget, nitrogen is less electronegative than oxygen. So when it is negatively charged, it's stronger base than alkoxide. The second thing that I have to tell you, obviously, I don't need two elimination. So I must have the right proportion. Two equivalent base for every equivalent. Now, that being said, if I was going to make terminal alkynes, the terminal alkynes, I must use three equivalent base. Even though I need two, if I want high yield, I must use three equivalent. What I mean, first, I want you to notice I am using three equivalent. Second, even though anytime we are doing chemical reactions, when we are using inorganic materials, at the end we use water to wash them, get rid of them. This time, water is mandatory. That's why I have written. You know, anytime you see anything on your arrow, it means these are reactants, guys, or solvent. In this case, obviously, water is not the right solvent. When water is not the right solvent. Stronger acid, weaker acid. So I don't want to neutralize like amide into ammonia. Ammonia is cheap, amide is not. Okay? So, when you see that, then it means, and when you see stepwise, it tells you it is reactant. So, for terminal, it is mandatory. Now, because the mechanism for both internal and terminal are alike, I will write the mechanism for terminal to explain why we do need three equivalents. I just want to make sure I am using ER. I could use CL as well. Okay. So first I am going to use my first equivalent of amide. Naturally, I have two leaving groups. Naturally, I have two protons that also will leave. Now, I want to ask you a question, guys, between hydrogen A and hydrogen B. Which of these two hydrogens would you expect to be attacked first? A or B? Oh, by the way, it doesn't mean you are not correct. You know, because you can be 50% correct by saying A. You can be 50 correct by saying B. So either of the two you pick, you have to explain. When you will pick A, B, you said B, am I correct? Why will you pick hydrogen B first, before A?
Because it's more acidic.
It is more acidic, why?
Because like it's more as property. It's closest to, I mean, compared to the A, it's less substituted.
Yes. Electron pushing groups decrease acidity. Hydrogen B, you have electron pushing group. Electron pushing group decrease acidity. That's the reason that commonly terminal hydrogens are more acidic than internal hydrogens when you have electron pushing. You know, everything else is the same. This group is taking electrons away from that one. This group is taking electrons away. So that is the same. Electron pushing decrease acidity. So the first thing will happen, you will take the hydrogen and you will kick out your leaving group. You get carbon-carbon double bond. So this is step 1. Now I have to do step 2. The second equivalent. I used two equivalent base. I get my product. That I said, if you want high yield, you have no choice. Did you hear what I said? You have no choice. You have to use 3 equivalent. Why is that? Then let's try and see what is happening. pKa 25. pKa 35. Now today, sodium amide was very expensive. I didn't have enough. And so I was trying to just use as much as I need, 2 equivalent. Now can I, before I add my sodium amide, can I tell to sodium amide, please remember, I really don't have a lot and I need this compound very badly. So just act as a reactant. And once you get my alkyne, don't do anymore. Can I help the sodium amide like that? Yes. Can I do it? But yes, it's very confident. That will sodium amide lessen. That's the problem. You and I cannot stop acid-base reaction. Stronger acid liberates weaker acid. Chemical reaction occurs one molecule at a time, not one mole. Do I have to remind you of Avogadro now? So anytime you are using any amount, no matter how small it is, you have millions of molecules. So one molecule is formed. As soon as this formed, then what will happen? Remember, stronger acid, stronger base. You can go either way, by the way, guys. Stronger base liberates weaker acid. Stronger, again I repeat, stronger base liberates weaker base. Stronger acid liberates weaker acid. So any way you want to consider it, don't forget everything is a relative. Between ammonia and amide negatively charged is stronger base. Again, I repeat, sorry guys, okay? So, stronger acid produces stronger acid liberates weaker acid. Stronger base liberates weaker base. So any way you look at it, in chemistry we cannot, again I repeat, we cannot stop acid-base reaction. So whether I like it or not, this kind of reaction happens. So as you see, 1/3 of base, do you agree? 1/3 of base is being wasted, and I have no control over it. But nonetheless, I want to make alkyne. So if I want to make alkyne, what do I have to do? Stronger acid liberates weaker acid. pKa of water. Do you remember pKa water? Yeah, it is. I don't want exact. It is 15.74. 16 is good enough. Okay, guys? Around 16. Remember. So stronger acid liberates weaker acid. Stronger base liberates weaker base. Anyway, you want it. So that's why first water is mandatory. If you don't have water, you are not going to have terminal alkyne. Internal, we don't have this problem. Because with internal alkyne, you do not have that kind of acidic hydrogen bonded to your carbon. So this is the main reason.
Yeah, internal have no hydrogen.
That's what I'm saying. You don't have. No,
Okay.
I cannot say internal doesn't have hydrogen. I say internal hydrogen does not have that kind of hydrogen. And because no matter what organic compounds, they always have hydrogen. Your carbon of all kind doesn't have hydrogen. The neighboring carbons have hydrogen. So you have to be very careful about the vocabulary. That's why I said internal alkynes do not have that kind of acidic hydrogen that I be concerned. Terminal, they have. So with terminal, you and I have no choice. But that being said, as a matter of fact, this acidity is tremendously helping us to make larger alkynes that they have also different functional group. What am I talking about?
Professor?
Yes,
So why do we need the third equivalent?
because I don't have control over the behavior of the molecule. Okay. This is a reaction cannot be stopped. That's what I said. Even I begged the AMAG, do not react. It didn't listen to me. I don't have control over it. It happens. Acid base. Again, I repeat, pK-825, pK-835. Strong acid liberates weak acid. That's the principle of organic chemistry, general chemistry, organic chemistry. These are principles, guys. These are not organic factors. It's the same thing. For example, because this is but on the other hand, you take what's the answer? No reaction. Because if there was a reaction, a weak acid should make HCl, which it is strong acid. Okay. So these are principles of chemistry, guys, not organic chemistry. And that's why I said it has become slogan. Strong acid liberates weak acid. If that was not the case, it wouldn't become slogan. So now, that being said, when it comes to organic chemistry, truly we get advantage of this relative acidity of basicity. So I can use larger I will call them not terminal, internal. Strong. Terminal. So the fact that the hydrogen of alkyne is acidic enough that it can be taken away by a strong base. I'm so glad that you are truly, and I mean it sincerely, and that you are watching my action and correcting me. Thank you so much. So due to the fact that these terminal alkynes are acidic enough that we can take the proton away, we use them to make organometallic compound. In chemistry, when we are saying organometallic compound, we mean a molecule that it has carbon, hydrogen, and metal. Again, chapter 8. You learned Grignard reagent. Grignard reagent is organometallic compound. Carbon, hydrogen, magnesium. Organolithium, same story. Carbon, hydrogen, lithium. So, another way of making organometallic, you already learned how to make a Grignard. You already learned how to make organolithium. Chapter 8, you can always go back, read. Now, another way of making organometallic compound is from alkanes. Not any kind of alkanes, of course, it has to be terminal. So we can take and treat it either with sodium amide, lithium amide, depending on whether we want sodium or lithium, and generate basically any base that it is stronger. Any base that it is stronger than this base. Now, once you have this organometallic, you can use this organometallic exactly the same way that you were using Grignard or organolithium. Okay, yes? These organometallic compounds can be used exactly the same way. There is no difference between them. They act exactly the same. So what am I talking about? I can react for SN2 reaction. These are very strong nucleophile, as well as strong bases, by the way. So I can make internal alkynes from terminal. Not only I can react them with haloalkanes, again I said you can use this exactly the way that you were using organolithium or Grignard. So what I mean that I can react this with an aldehyde. Either THF, don't forget, when you have this kind of organometallic compound, commonly you will use ethers, THF, or anything. So, you can make compounds that they have two functional groups, carbon-carbon triple bond, or carbon. So basically, you can react them with aldehydes, ketones, anything you want. So I will give you one more reaction, and I'm going to ask you to write major organic product. this reaction. I hope you are noticing I am using a pulsar. Okay? Naturally, your nucleophile is going to attack one of these two carbons. And my question is, I am going to label the two carbons. Which of the two would you expect to attack faster, A or B? Yes. Why? Because you are doing SN2. In SN2, less substituted carbon. Don't forget, these are strong nucleophiles. They go by SN2. So it is going to be least substituted. That's why they are. Ring opening, remember, is a stereo and radio selective. Don't forget that. So when it comes to this one, obviously, you are going to have CH2, CH, OH, CH3. Question. What are you going to write here? Did you write plus enantiomer? Yes. Did you write plus enantiomer or plus diastereomer? Yes or no? Why not?
Well, our kind don't really have stereochemistry because they're 180 degrees. So they wouldn't have.
Well, this was correct, not the answer. Okay. The answer is you are not generating a stereocenter. Is that yes? Because this is your stereocenter. It's the same as stereocenter. You are not generating an stereocenter. And that's the reason. And don't forget, it's not only alkyne, it's also the other party. We have to keep all of those in mind. So, thank you for staying a few minutes late. On Tuesday, we will finish chapter 13 for sure. And don't forget, the exam that you are going to take a week from today covers those 3 chapters plus NMR spectroscopy. Have a nice weekend.